Welcome to homework.
In this exercise, we have a proposed solution for the Schrodinger equation for the harmonic oscillator. The solution, psi 0, is equal to A0, this is just a normalization constant, times the exponential of minus alpha squared x squared divided by 2, where alpha squared is m, the mass of the oscillator, times omega divided by h bar. And I've also written here the Schrodinger equation for the harmonic oscillator. Notice that the potential here is the potential of a harmonic oscillator. It's 1/2 of m omega squared x squared. Omega is the angular frequency of the oscillator. And also we have the energy levels for the harmonic oscillator, En, which is equal to h bar omega times n plus 1/2. And in question A, you have to show that the proposed solution is indeed a solution for Schrodinger's equation for the harmonic oscillator with an energy that corresponds to n equals 0. So basically, I'm going to take the solution, the proposed solution, and I'm going to apply this wave function to the left-hand side of Schrodinger's equation, this part here. And I'm going to show that it agrees with the right-hand side. So basically, we have to take the derivative of psi 0 with respect to x, actually the second derivative, okay, and in order to apply this into the Schrodinger's equation. So let's start by that. Notice that this is equal to d dx of the derivative, which is equal to minus alpha squared times x times a0 e to the minus alpha squared x squared divided by 2. So this is the derivative. Sorry. This is the derivative of minus alpha squared x times psi 0. Okay, so this is the derivative of psi 0 times minus alpha squared x plus, actually minus alpha squared times psi 0. And here I've already taken the derivative of x. Now notice that the derivative of psi 0 is just this thing here. Okay, so it's equal to minus a squared, alpha squared x times psi 0 times minus alpha squared x minus alpha squared psi 0. So this is equal to alpha to the 4th x squared psi 0. So let me isolate psi 0 here. So I have minus alpha squared times psi 0. So this is the value of d2 psi 0 dx squared. And I'm going to substitute alpha squared for m omega over h bar. So I have m omega over h bar, all of this squared, x squared, minus m omega over h psi 0. Now the left-hand side of the equation is minus h bar squared over 2m times m squared omega squared over h bar squared x squared minus m omega over h bar, all this times psi 0 plus 1/2 of m omega squared x squared psi 0. Okay, so notice that this is equal to minus m omega squared x squared over 2 psi 0 plus h bar omega over 2 psi 0 plus 1/2 of m omega squared x squared psi 0. So these two terms cancel. And we're left with h bar omega over 2 psi 0. And we want this to be equal to the energy times psi 0 if this is truly a solution. And it is a solution as long as the energy is equal to h bar over 2 times omega. And this is exactly the energy of the harmonic oscillator when n is equal to 0. If we just look back here, if n is set to 0, then the energy of the harmonic oscillator is h bar omega over 2. Then in question B, you have to find the normalization constant, A. So remember that normalization implies that the integral from minus infinity to infinity of psi squared dx is equal to 1. Now psi is equal to a0 squared times e to the minus alpha squared x squared dx. So this must be equal to 1. Now this integral here, if you look it up in a table of integrals, is equal to the square root of pi divided by alpha. So you get that the absolute value of a0 squared times the square root of pi over alpha is equal to 1. So this means that a0 squared is equal to alpha squared over pi to the 1/2. a0 is equal to alpha squared over pi to the 1/4, and alpha squared is m omega over h bar. This is the value of a0. This is the normalization constant. Finally, in question C, we have to find the classical turning points, and also what is the value of x for which the probability density is maximum. Now, notice that the classical turning points happen when the potential energy U is equal to the total energy. Okay, so U of x is equal to the total energy. In our case, U of x is 1/2 of m omega squared times x squared. I'm indexing the turning point by xt, and this must be equal to the total energy, which is h bar omega over 2. Okay, so the turning points xt are equal to plus or minus the square root of h bar divided by mass times omega. Okay, these are the classical turning points. And the point for which the probability density is highest remember that the probability density is equal to the square of the absolute value of the wave function, so it's a0 squared times e to the minus a squared x squared. Notice that this is smaller or equal to a0 squared, and the equality happens when x is equal to 0. Okay, in that case, the probability density is equal to a0 squared. So the maximum of the probability density happens when x is equal to 0. This is exactly what we wanted to show, which concludes our exercise.